Hi everyone. Today we're going to talk about Lesson 8 in our Quantum Theory and Periodicity chapter. And Lesson 8 deals with periodic trends, just like we were talking about last week when we talked about atomic and ionic radius. This time we're going to be talking about something called ionization energy. So if you think about the term ionization energy, it has the word ion in it. And essentially what ionization energy is the amount of energy required to turn an atom into an ion by removing an electron. So we're essentially creating these positively charged ions by ripping off an electron. So if you look at this chart, you'll see this is a chart of first ionization energies. So we say the term first because technically you can continue to remove electrons. And that would be called second ionization and third and fourth ionization. And we'll talk about successive ionization energies in a few minutes. But for now, let's focus on the first ionization energy, which is the energy required to remove the most loosely held, that very first electron from an atom. Now, if you look at the graph, you'll notice a pattern. So across the graph, what I want you to pick out is that each one of these lines represents a period on the periodic table. So I'm going to go through and label these different periods for us. Okay, and just like that, I've labeled all of the periods, at least the first and last element in each of the periods. So first I'd like to consider a group on the periodic table. So let's look at the group that includes hydrogen, lithium, sodium, potassium, rubidium. That's all of the elements that are at the bottom of each of these lines. The one thing that we talked about last week is that the atomic radius of these increases because of an increase in the number of energy levels and an increase in electron shielding. Today, we're recognizing that ionization energy does exactly the opposite. Ionization energy decreases for each of these elements. And the reason is it becomes easier to remove an electron from an atom where the electron is further away from the nucleus and where the electron is more shielded from the attractive forces of the nucleus. So we would expect the lowest ionization energies of any group on the periodic table to occur for the elements that are closest to the bottom of the periodic table, and we would expect the highest ionization energies for any element in a group or a family to occur near the top. If we consider the trend observed across a period from left to right, we will also see a pattern that is opposite of what we saw last week. So last week, we said atomic radius decreased across the period due to an increase in effective nuclear charge, or what we're calling the strength of the nucleus. Here, we see the opposite pattern. In fact, because the nucleus is stronger for elements on the right side of the table, more energy is going to be required to remove that electron. First, the electron is closer to the nucleus because the atom is smaller, and second, because of an increase in the number of protons, it becomes more difficult to remove an electron from this tight, compact, really strong atom. There are a few hiccups that occur along the way. Let me identify those for you. These anomalies, which I have identified with a blue circle, occur after the second and fifth element in each group. And they are the result of a certain stability that is offered by having a completely filled sublevel or a half-filled sublevel, something that we've talked about earlier when we were talking about orbital notation. So if you notice, going from beryllium, the second element in the second period, to boron, the third element in the second period, the energy required to remove an electron actually goes down instead of following that pattern straight up. It is easier to remove an electron from boron because the 2p sublevel is filled with just one electron. That makes it partially filled, the least stable of our four possibilities. We see that same anomaly occur in the third period. As we go from magnesium to aluminum, we see that it requires more energy to remove an electron from an atom of magnesium than it does from aluminum, even though aluminum has more protons. Again, this occurs because the 3p sublevel in aluminum is partially filled, which makes it slightly less stable than the completely filled 3s sublevel found in magnesium. We see a similar anomaly when we get to the 5th and 6th elements. The 5th element in the second period is nitrogen. The amount of energy required to remove an electron from nitrogen is slightly higher than the amount of energy required to remove an electron from oxygen. This is because nitrogen has a half-filled 2p sublevel, and oxygen has a partially filled sublevel with 4 electrons in it. The partially filled orbital slightly destabilizes that and allows for an electron to be removed more easily. We see the same pattern going from phosphorus to sulfur in period 3. It's easier to remove an electron from a partially filled 3p sublevel in sulfur than from a half-filled 3p sublevel, which is what we find with phosphorus. So let's summarize what we've found so far. The trend for ionization energy within a group from bottom to top is that ionization energy will increase. We see an increase in ionization energy bottom to top for 2 reasons. Number 1, electrons in atoms at the top of a group are closer to the nucleus. And number 2, electrons in atoms at the top of a group are exposed to less electron shielding. There are less electrons in the way, blocking the nucleus from attracting those outermost electrons. Now let's re-examine the trend across the period from left to right. We find that ionization energy increases as you go from left to right, meaning the noble gases have the highest ionization energies in their group. It requires more energy to remove an electron from a noble gas than any other element in that same period. The second reason why it is more difficult to remove an electron from an atom on the right side of the table is that the nucleus is stronger. There is a greater effective nuclear charge due to an increase in the number of protons. Please have a look at this completed slide. If you have any questions, please jot them down so you can ask them during office hours. The table you see now shows successive ionization energies for elements in the third period of the periodic table. What you'll notice is a yellow kind of staircase going across the table. The staircase shows where the electrons are emptying out of the valence shell. Let's look at a single element. If we consider the element sodium, what is listed as 1 IE represents the first ionization energy, or the amount of energy required to remove the first electron. Where it says 2 IE, that's the amount of energy that is now required to remove a second electron. Third ionization energy, fourth ionization energy, and so on. You'll notice that the pattern only goes up. After the removal of an electron, the cost to remove the next electron is always going to be greater. And that is due to an increase in the proton to electron ratio. If we look at sodium, you'll notice that it costs 496 kilojoules to remove the first electron, converting that sodium atom into a sodium plus ion. However, removing the second electron costs almost 10 times as much, 4,560. The reason is sodium has 1 valence electron, so that 1 electron can be removed fairly easily. However, when we go to remove a second electron, we're breaking up a full energy level. So it costs us a lot more energy to remove a second electron from sodium. That jump in ionization energy can actually help us predict how many valence electrons an unknown atom would have. Let's take a look at a second example. In our second example, we're going to look at magnesium, an element in group 2 on the periodic table. First, notice how the energy required to remove an electron only increases, just like we saw in sodium. Again, the reason for this is that the proton to electron ratio is increasing, meaning the number of protons is remaining the same, but those same number of protons are holding on to fewer and fewer electrons. So they're going to be able to hold on to them tighter. Therefore, every additional electron that is removed is going to require more energy. Let's look at removing electrons from magnesium. Removing the first electron costs us 738 kilojoules. Of course, removing the second electron is going to require more energy because of the proton to electron ratio, but it only goes up to 1,450 kilojoules. However, when we try and remove a third electron from magnesium and form the magnesium 3+ ion, we go up by almost a factor of 5. And the reason is magnesium has 2 valence electrons, so it's able to lose 2 electrons relatively easily. The result at this point is a very stable noble gas configuration. Removing a third electron from magnesium requires a substantial greater amount of energy. As you can see by looking at the 2 highlighted cells on the table for each element, the top cell represents the amount of energy required to get to that very stable noble gas configuration. The second cell that is highlighted, the lower cell, represents how much additional energy you would need to put in order to break that noble gas configuration. Notice that those amounts go up as the number of protons go up as well. This wraps up our lesson on ionization energy. At this point, I would like you to make note of any questions that you have and consider posting them in the forum at the top of Unit 3 folder, or ask them at our office hours. Thank you, everyone. In our next lesson, we will look at electronegativity and electron affinity trends. Hope everyone's having a great week. See ya.